we're going to kind of extend our derivative knowledge is something called the chain rule. And the short of it is the chain rule is used when you have a function within a function, thus seeing the fog. Okay, it's because it's not that we're really doing fog and composing functions, but we're going to see functions within functions. So the chain rule is used to differentiate composite functions such as y equals the square root of x cubed plus 2, or y equals the sine of x squared. And so the idea here is that, oh, I have the square root of something. That's something to the 1/2 power. That's a derivative we have to take. But then there also is inside of it an x cubed plus 2. Oh, I have to take the derivative of x cubed also. Okay, or x cubed plus 2. You know, sine x, we have a derivative for sine, but we also have a derivative for x squared. And so it's how do we handle these when these functions are composed together. So remember, you create a composite function by plugging one function into another, thus the fog and goff. We can find the derivative of each separate function by using the rules we've learned so far, but we need the chain rule to find the derivative of two functions plugged into each other. Okay, so it's how do we handle the compositions. Now, the rule here. If f and g are differentiable, then the composite function, f composed with g of x, fog, which is also f of g of x, is differentiable, and f prime of g of x times g prime of x. Now, the short of that is the derivative of the outside times the derivative of the inside. Okay, so what you'll see me talk about doing is I'm going to do the derivative of the outside, whatever my outside function is, leaving the inside as is. And then times, and then we're going to take just the inside and do the derivative of that. Okay? Leibniz notation will allow us to use u substitution. Let y equal f of u and u equals g of x. Notice that y is a function of u and u is a function of x. So it follows, and they say dy dx, the derivative of y with respect to x, is the derivative of y with respect to u times the derivative of u with respect to x. It's just the same, another way to say it, okay? I'll be honest, we don't use that notation as much, okay? At least not for showing this. Basic. Multiply the derivative of the inside function by the derivative of the outside function. Okay? And so we're going to talk about this. Let's look at example 1. Find the derivative of f of x equals 5x plus 3 quantity squared with and without the chain rule. Okay, so without the chain rule. For Unit 2 exam, in order to find the derivative of this, what would I have said needs to happen first? You're going to have to FOIL this out first, okay, before you can take the derivative. So the idea that f of x is 5x plus 3 times 5x plus 3, well, if I FOIL that out, I'm at what? 25x squared plus 30x plus 9. Are you guys with them? I'm with them. Now, so then based on if you FOIL it out first, now the derivative. These are basics. I think we know these basics. Derivative of 25x squared plus derivative of 30x plus derivative of 9. 0. So 50x plus 30, yes? Mm-hmm. Okay. Now, I say that's the old way. You can still always go back and do that. Okay? Here's the deal. We have chain rule as an option on this one. There's some scenarios where chain rule is not an option, it's required. So that's, you know, it can't just be, oh, well, I'll always just go back and use the old methods. It won't always work. This is just one of those scenarios where it is. So now, with the chain rule, so let me write, our original function is f of x equals 5x plus 3 raised to the second. the chain rule, if you looked up above, it first said f prime of x, g of x. So what they're saying there is the derivative of the outside. We leave the inside the same. So as you look at this, what is the outside function that's going on here? This is something raised to the second power, yes? So the outside function is that something raised to the second power. How do you take the derivative of something raised to the second power? You multiply, you move the 2 out front, yes? And then what's my exponent become?
1.
1, yes? Now, the idea here is that inside 5x plus 3, it just stays for the moment. Okay, it's just going to stay for the moment. Now, times. So right now we did the derivative of the outside. Something raised to the second is 2 times that something to the first. And now it's times, if you look up above, it's g prime of x, the inside. What's my inside function? 5x plus 3. What's the derivative of 5x plus 3? 5. Now, that's your derivative. Let me prove to you it's the same if we clean it up. Are we seeing it? If we go ahead and put together 2 times 5, 2 times 5 is 10 times 5x plus 3 to the first, but I don't really need the first, do I? And if you distribute the 10, we're going to have 50x plus 30, yes? Okay, now, on this one you may be like, ugh, that was annoying, that was more work, it made me think more. Okay, but there are times that it's gonna be the way to go, okay? In terms of how to leave your answer, any of these would work. I mean, technically, you could leave your answer like that. That's the annoying one to me. But technically, you could, and I think most of the time, do we just take the derivative and stop? No, usually you're doing something else with it then. But any of these would work. We could have also distributed the 2 and then multiplied the 5 in. Is that what you did? And that's what, now that I look at my notes, that's what I did in my notes, is like right here, I said, okay, if I distribute the 2 in, it's 10x plus 6, and then times the 5, which takes you there. Those are all options, okay? My point was to show you they're the same. Okay, so example 2. Find f prime of x, given that f of x is 4 minus x squared raised to the power of 3. And for whatever reason on this one, it's written out as derivative of the outside times derivative of the inside. Get my pages up, I want to see. Okay. Now, with that in mind, what is your outside function? Or maybe I should ask, what's the inside function? Is that an easier question? Okay. So can we agree with Tate the inside function is 4 minus x squared? If that's the inside function, what's the outside function?
Power to 3.
Something to the power of 3. And a lot of times you'll hear me say that I'll say something to the power of 3. Okay? So, and I'm just going to write it as x to the third. So when we do the derivative of the outside, you're doing basically the derivative of x to the third, but it's not just saying x on the inside, it's that other piece. Okay? So, let's go over here and try this. Derivative of outside function. So the outside is something to the third. Just keep the something the same. How do we do derivative of something to the third? Move the 3 out front.
4 minus x to the power of 2 to the power of.
Are you guys okay with what he did there? That's the derivative of the outside. That inside piece, I didn't change it. And now times derivative of the inside.
Negative 2x.
So derivative of 4 minus x squared is negative 2x. I figured I'd probably put this in parentheses because I don't want it to look like a minus 2x. I want to make sure it's timesing. You technically could leave it like that. I would encourage one cleanup step here. I'm not going to multiply it all out. But we have this 3 multiplied out front, and I have this negative 2x multiplied out back. I would clean those up and put them together. 3 times negative 2x is negative 6x, and then times 4 minus x squared quantity squared. I personally would leave it like that. Okay. However, if you get industrious and want to FOIL that out and then distribute in, I don't think any of us have that much time in our lives right now. So, okay. Moving on. Let's continue to practice. So, this is just, I'm honestly not even really sure quite why this is in here, but the idea that of how we can work chain rule with the power rule. Okay, so the idea that if, assuming the inside is differentiable, g of x raised to the n. This is what we kind of just did, right? We move the power out front, subtract 1 from the power, that inside stays the same, and then it's going to be times the derivative of whatever that inside was. Okay. The other one that we're getting ready to talk about is the derivative of e to some power. Well, what do we know about the derivative of e to the x? Derivative of e to the x is e to the x. So derivative of e to some power is still e to some power, but then you have to do the derivative of the power. Okay? And we'll talk about that, down on example D it looks like. Okay, let's try A. F of x equals the square root of x squared minus 1 raised to the third.
X squared minus 1 to the 3x.
Okay, you need to rewrite this before you start it. Because as it is, do we do derivatives of square roots? No, we change them to powers, yes? So we need to do a rewrite. If I rewrite this, this is f of x equals x squared minus 1 to the 3 halves, yes? Okay. Derivative of the outside. What's my outside?
3 halves.
3 halves. So how do I do the derivative of the power of 3 halves? We're going to put the 3 halves out front. Then what? Inside stays. X squared minus 1 stays as is.
1 half.
Subtract 1 from the power, and we're at 1 half. Times the derivative of the inside, which is?
2x. Sorry.
2x. You guys were all starting to agree on 2, and I got a little concerned. Derivative of x squared is 2x.
Yeah.
Okay. I would clean it up a little bit. If you clean it up, there's something nice that will happen. Do you see it?
Oh, 3.
What happens when you multiply 3 halves and 2x?
3x.
The 2's cancel, right? 3 halves times 2x. I can cancel my 2's, so I'm going to be at 3x. So 3x. Could leave it as times x squared minus 1 to the 1 half. Did I leave it like that, or did I put it back to square root? I have it both ways. The other option is, could you take that 1/2 back to a square root? You could. You could say 3x times the square root of x squared minus 1. I like either the bottom row or the next to bottom row. Okay. B.
You're gonna say quotient rule.
Nope.
2x minus 3 to the negative second.
Yeah. I'm not going to say quotient rule just because on top -7 is just a constant. And so that makes it easy to work with. If -7 on top was something, if it had a variable in there, I would be talking quotient rule. But since it doesn't, bringing that denominator up, this is -7 times 2x minus 3 to the -2nd power. And then that -7 just acts like a coefficient.
How did you just bring it to the top?
Because I changed the exponent to a negative. Remember, the 1 over x is equivalent to x to the negative first. If it's just an x in the denominator, x to the first, it's a negative exponent when you bring it across the fraction bar. Okay? Okay. Outside function.
14
Uh-huh.
and
3.
2x minus 3. That's it. Times
2.
You guys okay with that? Okay.
It's just 28 times 2x minus 3. Oh, we still have the -3.
So I definitely 2 times 14 would be 28 times 2x minus 3 to -3rd. I don't officially know. A few of you left negative exponents in a few spots on test and I let it go. I would be careful about leaving negative exponents, okay? Because I'm not sure that they will want that. How can I rewrite this without a negative exponent?
28 over 2 times 3.
28 stays on top. 2x minus 3 to the -3rd goes to the denominator with a +3rd. Okay. Got it? Okay, moving on then. Stop me where you need to. C. 5 minus 4x squared raised to the 2/3. Where are you starting here?
2/3 and 1/3.
Okay, power moves out front. That's my out front, 2/3. What's inside my parentheses? 5 minus 4x squared. What's my power?
-1/3.
2/3 minus 1, so 2/3 minus 3/3, -1/3. Am I done? Of course not.
Times -8x.
Okay. Derivative of the outside, which was the 2/3 power, times derivative of the inside, which is -8x. Trying to debate how I would clean this up, and yeah.
Just leave it like that?
No.
-8x minus 2/3.
First of all, can we put the 2/3 and -8x together?
Yeah.
Yeah, that's going to be what?
-16x over 3.
-16x over 3 times that minus 4x squared raised to the -1/3. I'm going to say do one more thing.
Take it to the bottom.
Uh-huh.
Take it to the bottom. Oh, for the negative 16 over 3 times 5 plus 4x squared.
Did Tate put an X in his? I didn't hear the X.
For what? 4x squared?
No, with the 16.
No.
That was the one part I didn't hear you say. So negative 16x stays on top. So that was the top of the fraction. 3 is the denominator of the fraction. So that's the denominator. And then that negative 1/3, because it's a negative, to make it positive, we move it to the denominator. The only other difference I have in my notes is I have it as a cube root. Not saying you have to have it as a cube root. But that is the only other difference, is you could have it as a cube root. Okay. D. It is different. So we're trying to do the derivative of e to the 3x squared. So overall outside function, so to speak, I don't know if I call it outside or not, but the big picture is this is e to some power. What's the derivative of e to some power?
E to the power.
E to that power. E to some power. So e to the 3x squared. Then what are we going to have to multiply by? The derivative of some power.
So 3x squared.
So derivative of 3x squared, which is
6x.
6x. I personally don't like to leave it like that.
Is the 6x the... Oh, it's the inside?
It's the inside, yes. So e to some power being the outside, and then the power being the inside.
So most of the time, the x is always going to be on the inside.
What?
There's going to be some x on the inside.
Some sort of x on the inside.
Mm-hmm. Yeah. Okay. I would suggest rewriting this as 6x e to the 3x squared is your most common way to write that. Okay. Not that the 6x can't be out back. Are we okay with that one?
Yeah.
The first e always, you know.
Yeah.
Okay. Continuing until you pause me, or until you ask questions. E.
Oh. 22 times 6x plus 3 to the negative 1/3.
I'm with them. Are you? It's a cube root, so that's a 1/3 power. It's in the denominator, so it becomes negative. Okay.
Negative 2/3. No, positive 2/3.
Multiply the negative 1/3 out front. Negative 1/3 times negative 2 is going to be positive 2/3. Inside stays the same. Power.
Negative 4/3.
Subtract 1 and you're at negative 4/3. So we did derivative of the outside, which was the negative 1/3 power. Times 6. Derivative of 6x plus 3 is 6.
Four.
2/3 times 6 is 4. So 4 times 6x plus 3 to the negative 4/3.
6x plus 3.
Okay, leave that 4 on top. 4 over 6x plus 3 to the 4/3 power. Okay. You could, if you wanted to, make that the cube root of 6x plus 3 to the 4th, but Okay. F. I'm going to call this the first challenge problem.
Yeah, I got you.
Now, let me ask before we get going too far. What is this 3? This 3.
It's like x to the third.
Okay, it's x to the 3rd. So this is cosine cubed, right? So I'm going to rewrite this as cosine of e to the 5 theta quantity cubed. Because so remember, when we have functions squared, okay, so for instance, if you have sine squared x, you can write it as sine squared x, or you can write it as sine x quantity squared. Remember that sine x squared, that's something different. That is not the same. These two are the same. This one is something different. So just kind of remember that, okay? Now, so this is cosine cubed of e to the 5 theta. So that e to the 5 theta is where we normally just have an x or a theta. Our variable on the inside is e to the 5 theta. Okay? So, what is our most outside function?
Something to the 3rd.
Something to the 3rd. So, how do we do the derivative of something to the 3rd? Move the 3 out front. And then it's going to be times, you keep the inside the same, cosine e to the 5 theta, and the cosine is raised to the 2nd. Times.
Wait, what did I just...
What's the next most outside function?
Cosine.
The cosine. So overall, it's something to the 3rd. Well, that something to the 3rd is a cosine to the 3rd. So how do you do the derivative of cosine of something? The derivative of cosine of something is negative sine of something. So now I'm going to say times the derivative of cosine of something is negative sine of what is my current inside? E to the 5 theta. Now, so it was cosine to the 3rd. We took the derivative of cosine of something. Now, the derivative of negative sine of something, we did the derivative of cosine of something, got negative sine of something. What's my something? E to the 5 theta. Now, if this was just a variable theta or x, we'd be done. Because the variable of theta or x has a derivative of 1. But what's the derivative of e to the 5 theta? Derivative of e to some power is e to some power. Now,
you have to keep going taking.
you have to keep going until there's no more derivatives to take. We've got one more. So derivative of e to some power is e to some power. What about this power? What's the derivative of 5 theta?
5.
It's like asking what's the derivative of 5x? 5. Sorry. Too late warning, write small. So that's like the chain rule 3 times.
No.
So that's why it's called that,
Okay?
right?
Because you can keep adding links, so to speak. Yes. Okay. Now, basic cleanup. There's only so much we can do here. What I do see, I see a 3 that can go out front, times a 5 that can go out front, times a negative that can go out front. Okay? So I'm going to write mine. 3 times 5 times a negative is Negative 15. I might go ahead and put e to the 5 pi, or 5 theta, out front. And then the other two, I don't think it really matters. I have times sine of e to the 5 theta. And then times cosine of e to the 5 theta quantity squared. Oh, that's what I did do. Where could we put that squared at if we wanted to now? Could you put it on the cosine? It's cosine squared of e to the 5 theta. If that works better for you, you can do that. So that too could be there, or it could be outside.
That was our fun. Thank God. Yes.
Okay. So 1 chain rule is normal. 3 chain rules, it happens. It's not the norm though. Okay. So we'll continue practicing tomorrow. I think we have a whole nother page of practice and then a little bit of chart practice on the back. No, I feel like we should be able to knock that out pretty quickly.
Oh my gosh, work done?
I don't know. I hate to say that because anytime I say that, it doesn't come true. I already jinxed pre-calc for tomorrow because I said there should be work time, and we'll see.